Let's take a look at this optimization problem from the 4-5 homework. It's giving us a specific box to begin with, and then it wants us to solve in general if the figure is a square. What we're trying to do is optimize the size of the volume of a box given the dimensions of a piece of cardboard that we're using to create it. In this case, we have a piece of cardboard that's 27 by 15. Now, I know if I'm going to fold up a flat piece of cardboard, then the sides have to come up, both the length and the widths have to fold upward. So we know each of these, both the length and the width, each of the sides, it's going to have to be folded up a length of, or for a height of x. I'm letting x represent the height of the box. So the length is going to have 27 minus x on this side minus x on this side. The length is going to end up being 27 minus 2x. Similarly, the width of the box, it's losing x feet on the left-hand side and x feet on the right-hand side when you use it to construct the box. So the width is going to be 15 minus 2x, and then of course our height being x. So this enabled me to get a volume for the box created from this cardboard base of dimensions 27 by 15. Now, I went ahead and I foiled out the length and width expressions, and I got my 405, and then I would have minus 54x minus 30x for a total of minus 84x. Then we have plus 4x squared. Of course, now we have to distribute the x through all of those terms. That's where this comes from. This is the volume of my box. Now, it's also worth mentioning here, you'll need to make sense out of your solutions. We can't have an x that's not a reasonable value. That's why I called this the reasonable domain. So think about this. You can't fold your box up to a certain height that would enable it to not even have any width. So I said, well, imagine what if you wanted a box of a height of 7.5 feet? Well, you'd have to fold this up 7.5, fold up this 7.5. You wouldn't have anything left for the width of the box. So in fact, it would just be a sheet in the other direction. So now we can say, well, okay, then the box is going to be anywhere from a minimum x is 0, and of course it can't include x is 0. So I'll say it's going to be the closed interval starting at 0 up to 7.5, or I should say the open interval starting at 0 up to 7.5. We can't include either of those endpoints because at those endpoints, you don't have a box. But instantly after 0, you have a box, and before 7.5, you would have a box. So I can say, okay, keeping in mind that domain for x, this is going to be the volume with respect to x. I need to take the derivative of that expression. And when I do, I get my 12x squared minus 168x plus 405. We set that equal to 0 to find our critical points. Now, critical points, not easy to find in this case. You could have done them graphically. I went back and just did the old quadratic formula. X equals negative b plus or minus the square root of b squared minus 4ac all over 2a. Now, when you do that and enter it into your calculator, the 168 plus this square root over 24 gave me the top answer, and then the 168 minus the square root over 24 gave me the bottom answer. The top answer I automatically discarded because it didn't fit the reasonable domain of this function. I wouldn't have a width if I tried to make the height 10.905. So I can say, okay, that's impossible. So then this one was possible. If I let the height be 3.905, I would have both a dimension left for the length and a dimension left for the width. So I can say, okay, that answer is fine. So then in order to find the maximum volume, I just evaluated my volume function right up here at 3.905, plug 3.905 in for x, and I got that answer. That was part A. Now, part B was more interesting here. It said that suppose that this original piece of cardboard, and we're supposed to forget the dimensions that they gave us, just suppose a square where we know that the width and length are equal to one another. Find the volume of the largest box that can be formed out of a square. Okay, so what I'm looking at in this case is similarly, I know I'm going to be folding up each side of the square because the height has to be uniform throughout. So I'm going to say, let's let, just like they said, each side of my square is going to be length S. Again, if I let X equal the height of my box, then both of my dimensions are going to be that length S minus 2 times the height for each side there, and of course the same thing here. So you'll see I said, well, the volume is going to be S minus 2x quantity squared times x. I squared out this group, gave me s squared minus 4sx plus 4x squared, all times x. I distributed my x through. Now, as I distributed my x through, I wanted to get this volume function in descending order with respect to x, which is the height of the box. So I can say, well, okay, then I'm going to get a 4x cubed, that's where this came from, minus 4 times s times x to the second, and then I would have plus s squared times x for the last term. Okay, now I have my volume formula. Just like the specific case, I need to take the derivative of that to be able to set it equal to 0 to find my critical points. Taking the derivative, I got 12x squared minus 8s times x to the first, and then I would have just plus s to the second for the third term there. When we set that equal to 0, I can say, well, all right, I can do that by quadratic formula again. So negative b plus or minus the square root of b squared minus 4 times a times c, where c is just s squared, it's a constant, all divided by 2 times a, 2 times 12. When I did this, I knew I needed to simplify the discriminant. 64s to the second minus 48s to the second ended up giving me 16s to the second inside that square root, which we know square root of 16s to the second is just going to be 4s. So I ended up with my numerator of 8s plus or minus 4s all over 24. Now, I didn't mention it earlier, but again, in this problem, you had to be thinking about a reasonable domain. Well, you know your height can't be more than half of the length of a side, because if it is, you don't have any dimension left to form the base of your box. So I can say, well, then I know x has to be less than half of s, because if x is equal to 2s, if x is equal to s over 2, then 0 would be the length of each side of your base. So I can say, well, okay, then the height of my box needs to start at 0, not including 0, and go up to, but not including, the length of my side s divided by 2. Okay, so now, with that in mind, I came down here and I said, well, if I evaluated 8s plus 4s, I get 12s. 12s over 24 is s over 2. That can't happen, because if the height is s over 2, then your base would be equal to 0. You wouldn't have a box. You see, that can't happen. That can't be in the domain. For my second one, if it's 8s minus 4s, I get 4s in the numerator over 24. That's going to reduce down to s over 6. I plugged that into my original volume equation, so I said, let's evaluate that volume at s over 6. That gave me 4 times s over 6 cubed minus 4s times s over 6 squared plus s squared times s over 6. When I simplified this, that first term, I had 4s cubed over 216, which reduced down to s cubed over 54. Then I had minus 4s cubed over 36. That reduced down to minus s cubed over 9. Then my last one, I had plus s cubed over 6. Combine those three terms, and you'll get a final fantastic answer of 2s cubed over 27. That would be the maximum dimensions of a cube. Sorry, I shouldn't say of a cube, of a box formed by a base that is a square. All right, hopefully that helped you out with this one. It's kind of a cool problem.